All right, we are now recording. We'll go to the current slide. And this is the end of where we were last time. Should have turned this on earlier, I forgot. We're doing quadratic surfaces, which is really an odd little feature that is thrown in here. I can remember when I was taking calculus, it's the first thing we did in Cal 1, and it was then called analytic geometry. And we started with that then and hardly used it again until sometime later. So now they put it in Cal 3 at the first, but we will have occasion to have the concepts there anyway. Now we did example 2, but the reason I'm starting here is that the example 3 is not in the slide set. So let's go back, and I think this is as good a place as any as to start example 3. All right. First, before we get started there, any questions on anything we've done so far? All right. Now, it says classify and sketch the surface. At least let's classify, okay? Here's the surface they give us, and they can write them in all sorts of different ways. What you have to do is figure out what this will wind up being. X minus y squared minus 4z squared is equal to 0. First it says classify. What I would suggest is rearrange, so it's going to be easier to classify. What would you suggest a way to rearrange this one? Any ideas? If I weren't in the room and you had to do it, what would be your first step? This is just a suggestion. Get the linear things on one side and the quadratic on the other. So what would that yield? In other words, let's add y squared and 4z squared to both sides. Okay, what would that give us? X is equal to, see that goes to 0, that goes to 0, y squared plus 4z squared. Now, this is assuming that you remember what these shapes are. Okay? This is first. Forget about x, and let's just consider it some constant. Okay? And here we have one, right? Okay. No, Davis. You have 2 first names or 2 last names. Okay? All right, Davis. Okay. All right. So let's just count x a constant for now. What would this shape be? If these two coefficients were the same, that would be a circle. Since they're different coefficients, this will be an ellipse. Exactly. So this is going to be an elliptical something or another. Now, what is it when, let's just say the z is constant here, what would this be? X is equal to y squared. Parabola, exactly. And this would be a parabola that would be opening on the x-axis because y could be plus or minus and going this way. And if y were a constant, what would that be? Parabola also. So this will be an elliptic paraboloid. Okay? Ellipse in one dimension and paraboloid in the other two. So it's an elliptic paraboloid. Okay? So there's the first. Elliptic paraboloid. Now if you're going to sketch it, ooh, boo hiss. Okay. I'll give it a shot here. All right, we're going to have, this is our x-axis, this is our y-axis, and this is the z-axis. I don't draw these things well, okay? But like I said, now, just looking at this side over here is always going to be what? Say again? No. Plus sign. Positive. Because that's squared and that's squared. This is always positive, right? No way this could be negative over here. So you're not going to have any negative x's. So I don't even have to draw the axis back here. Okay? Now with any x as a constant here, but positive, coming out this way, these are going to be, what did you call this? Ellipses. These will be ellipses. So for any constant x here, and by the way, when x equals 0, y has to be 0 and z has to be 0. No way around it. So the origin's going to be 1 point. And then, let's see, the major axis is the z. So it's going to be coming out something like this, coming like this. You know, these would be ellipses coming out the x-axis. Okay? Not very pretty. Okay? And then, going back this way, that would be an ellipse this way, I mean a parabola this way, and parabola this way. So if you can imagine some sort of shape like that, that would be, I'll set it backwards. I had the major axis here. This is the major axis, that's the minor axis. I had it backwards. This would be your elliptic paraboloid. Okay? And where the, yeah, right there. This surface is an elliptic parabola. Now, the better way to write it, and I didn't, but I probably should have, is to divide everything by 4. That might have made it look better. Okay? So divide this by 4, this by 4, and this by 4. Okay? Then you would have x over 4 is equal to y over 2 squared plus z squared, z over 1 squared. So in that case, you see y is the major axis here. I did it backwards. Should have had the ellipses go up that way. Okay. So, but anyway, it's the main thing is to see these are going to be ellipses this way and these will be parabola this way. But to get the major axis, I needed to divide. That's what I got it wrong. Okay. All right. Now, let me clear that, and there's a little bit of verbiage at the bottom of page 802, which is where example 3 was. Any questions before I clear it? Okay. Some second degree equations in x, y, and z do not represent the any of the basic types of quadratic surfaces. For instance, here's one. X squared plus y squared plus z squared is equal to 0. Okay? What is that going to be? Okay? Well, guess what? These three added together are always going to be positive, except they only add to 0. So there's only 1 point. Satisfy this. X equals 0, y equals 0, z equals 0. That's not a surface at all. It's a single point, the origin. That's all. You can't do anything else. If x were anything else, that couldn't be 0. If y were anything else, that couldn't be 0. If z was anything else, that couldn't be 0. So that's going to be a single point, sort of a dumb representation there. Okay? If you'd had something like this, x squared plus y squared is equal to 1, and you're told already that this is a three-dimensional surface rather than, if you just look at that, what's the first thing that comes to mind? That's a circle, okay? If you're in the plane. But if you're in space, then it's a circle in the plane, but then it goes infinitely in the z-axis. So that would be a cylindrical, right circular cylinder, okay? That follows the shape of that circle. So, yeah. They won't always be the other three. But we talked about cylinders before. Now, we also talked about, back when we did the generic form of the, there it was, right here. This is a generic form of a quadrant surface, okay? I said these terms, the cross terms here, take whatever shape it is and twist it in some way, okay? That's what these ones do. What the linear terms here do is displace the shape is still the shape, but they take it off the origin as the center and move it somewhere else. So that's what these forms do. And that's what the next thing we're going to look at is doing. Is this the one I was using? Okay, that's what I was using. Actually, I'll have more room if I go back and use this one, so I think I will. Okay. Classify and sketch this surface. X squared plus 2y squared plus z squared minus 4x minus 2 plus 4y, I can't read, minus 2z is equal to, no, plus 3 is equal to 0. Okay, let me make sure I got it right now. X squared plus 2y squared plus z squared minus 4x plus 4y minus 2z plus 3 equals 0. Okay. It says classify and sketch that surface. What would you do before you try to classify it? Just in general, what would be a good first step? Get it into tribes. Get your x's together, your y's together, and your z's together. And maybe put the constant on the other side. So let's do that. So this would be x squared minus 4x plus 2y squared plus 4y plus z squared minus 2z is equal to a negative 3. Now, it was something I was sort of trying to do, didn't get it done well. So I'm going to go back and regroup a little bit. Okay, this is x squared minus 4x. Okay, and 2y squared plus 4y. Okay, I meant to leave more gaps and spaces there. And here's why. Because these forms don't really do much for me like they are now. But I know one of your favorite activities of all times was completing a square. Remember how much fun we had with that? No, we don't. Okay. That's what we've got to do. We need to complete the square. And you remember the procedure? Take half of the b, a, b, c, of course here is 0. Take half of the b is negative 4. Half of that would be negative 2 in this square. Negative 2 squared is plus 4. So that would be plus 4. Okay? Now, I just added 4 to the left-hand side. I changed the formula unless I add 4 to the right as well. Right? Now, I'm going to go on and do this as a perfect square. That's going to be x minus 2 squared. Now here's how I knew that. As soon as I take half of this, that's what goes here. Half of -4 is -2. Okay. And the other reason I'm going to do this is because here I need this coefficient to be a 1. So what I'm going to do is factor out the 2 here and leave a y squared plus 2y. Plus, now here I can go on and complete the square here, I think. All right. Rachel?
Yes.
Okay. Okay. Good deal. All right. We're on, if you got a book, I don't know if you do or not, on page 803, example 4 of quadrant surfaces in space. What we're doing here, this was our original. First thing we did was group the x's together, the y's together, and the z's together, and left some blanks there. I completed the square on this one and got this, but when I completed the square, I added 4, so I had to add a 4 there. This one, I first factored out the 2 because to complete the square, I needed that to be the coefficient of 1. So I haven't done that one yet. I'm going to come back and do it. And this one, I can go and complete the square here. How does that go? Half of the b, half of -2 is? It's pretty easy. -1, square that, you get plus 1. Well, I just added 1 here, so I'd have to add another 1 there too, just to keep it the same function. Right? Now, so I know this is going to be z, and when I took half of this, it was -1 squared. So I've got that completed. I still have to complete this square, and how would I do this? Half of 2 is 1, and 1 squared is 1. So I'm going to add a 1 here, plus 1. But really, I didn't just add 1. Okay, and this, by the way, was equal to, that's 5 minus 3 is 2. Okay. I didn't just add 1 because we have a 2 out front here. 2 times 1 is 2, so I have to add another 2 over there. All right. And this becomes x minus 2 squared plus 2 times, and what would this one be, the perfect square? Y plus 1 squared plus z minus 1 squared is equal to 4. Okay. Now, to get it sort of in our most standard form, we divide everything by 4. I started to multiply. I don't know why I was going to do that. Okay. Divide everything by 4. But when we divide this by 4, 2 over 4 would be 2. And divide that by 4. Okay. This 2 disappeared. So I'm going to take it out of the picture altogether. Okay. I'm skipping some steps here because I don't have a lot of room. Okay. So this becomes now equal 1. Anyone want to know, make a guess of what this form is here? Anyone? Notice all the signs are pluses in front of the thing. So they were up there, they still are. Say again? Ellipsoid, you're absolutely right. If this was not there, this is an ellipse. This not there, that's an ellipse. This is not there, that's an ellipse. Everything's an ellipse, you know, in every trace. What do these do to it, though? This moves the center of the ellipse to x equal 2, y is equal to -1, z is equal to 1. So it moves the center x 2, y -1, Z plus 1. Okay, so it moves it up a little bit. Now, then we look at this. These two, if this isn't here, these two form circles. So those are in the XZ plane, that would be this plane, no, this plane, these are circles, and the other two planes there are actually ellipses. Ellipse is a special kind of a circle. So you do have a I can't hold this long, but I'll do it while I can. So you moved the center from the origin, positive 2 on X, minus 1 on Y, and plus 1 on Z. So there's your center. And in the XZ plane, and it's hard to see this, that is a circular shape there, XZ plane, but in the YZ and XZ plane, XY plane, these are ellipses. I can't hold it any longer. Okay. So that's an ellipsoid that is off-center. The center is 2, negative 1, 1. Make sense? Yay or nay? The fact that they're all pluses here means it's an ellipse. If all these denominators had been the same, that would have been a sphere, which is a special case of an ellipse. With this one being shorter, that means the y-axis is suppressed in both dimensions. You have this way it's an ellipse, and that way it's an ellipse. This way it's a circle. Okay. All right. Now, any questions on that? There's a little blurb on technology here that I don't have this form of technology, so I can't illustrate or show it to you, but if you do have access to, and this happens to be Mathematica is the program this is using, then by all means take a look at that. All right, good deal. Any questions? So let's move on to surfaces of revolution. Okay? The fifth special type of a surface you'll study, okay, if you think back, number one, I don't know the order of them. One, I believe, was a plane. One was a sphere. One was a cylinder. And then one was quadric surfaces. The fifth special type of surface is a surface of revolution. And back in 7.4, you studied the method for finding areas of such surfaces, which was, circling the arc length, around that circle. We'll now look at a procedure for finding the equation of that. So it says, consider the graph of the radius function. And I was trying to think. I'm trying to recall if there's really any need for this. I can't remember if I usually cover this or not. I think I tend to skip this one because if you think back at your syllabus, the course description said quadric surfaces. So we've actually done more because we did a little bit with cylinders and stuff, but this is beyond quadric surfaces. It's good stuff, but I'm trying to think if you're going to have any need for the surfaces of revolution. If you do, I'll apologize that we didn't cover it, but I can't think if I've ever, we do areas and volumes of them, but that was back in chapter 7, so I don't see any other reason. What they're doing now is coming up with the formulas for them, and I never use those formulas anyway, so I'm going to stop there and make the homework assignment from 11.6. We've already covered several of these. I would do all of 5 through 10. Now, only the odds have the answers in the back, but you should be able to identify all of these and match them with the figures that you see up above. Then you can look at the back of the book and get the odd numbers, and if you got the odds right, the odds are you got the evens right too. If you miss the odds, you obviously probably miss some of the evens as well. So I would do all those and come up with answers. Check your answers in the back for the odd ones. If you can't or don't know how to figure out how they got them, then go to calcchat.com, which is going to show you how to derive those. Okay. Then after you do that, do either 11 or 13. They're both at CalcChat. 11's at CalcView. Do any of the odds 15 through 25. They're all at CalcChat. 17's at CalcView. You can explore 27 or 29. And then the rest of those, I think, are finding equations for surfaces of revolution. So you don't have to do any more of those, I don't think. Let me just look down and make sure. I'd say over on number 49, do that one because that's not dealing with surfaces of revolution. It's using a hyperbolic paraboloid. And notice the difference between that and the one we did. This has a minus sign between the two squared terms, not a plus. Plus sign, that's the elliptic paraboloid. Minus sign is a hyperbolic paraboloid. And I think you might be able to do 51 if you choose to. You don't have to do that stuff. All right, 11.7 is not something we're going to do. They're really pretty good things, cylindrical and spherical coordinates, but it wasn't in the course description, so I don't really want to take class time doing them. It's good stuff, and if you do need that in your field of study, by all means go back and review that section. Now, speaking of reviews, the review exercises, since we didn't do the early part of 11, hopefully you did that in your Cal 2, nor did we do the very last. The only problems that you would probably find to do there would be any of the odds 49 through 57. I think that's all you'd have to do, 49 through 57. And those are also, those odds are at calcchat.com. There's a problem-solving section that if you're interested, by all means look at it. And I thought there was something else here. Oh yeah, no, I thought there was usually a chapter test at the end, but it doesn't have one, so too bad. All right, don't say there may be a few more problems you could look at. So let's now move to surface, vector value functions. Y'all okay with that? Now, the first test we have will be on Chapter 12, but I'll include one or two questions from Chapter 11, Section 11.6. Okay. All right. So we'll get started in 12.1. Goodness, I got me some caffeine at my break. I don't think it was enough. I think what I'm suffering from is hunger. I had breakfast around 6:30 or so this morning, and I've had true granola bars since. So I think that's why I'm running out of juice. And I think we're going to start at the current slide. Down there somewhere. Okay. Now, hopefully this picks up from wherever you were in Cal 2. If any of this is new to you and we need to go back to Chapter 11 and pick up some loose pieces, we can do that. For Chapter 12 is vector valued functions, whereas in Chapter 11 the title was Vectors in the Geometry of Space. So this is going to be vector valued functions. 12.1 is also entitled Vector Valued Functions. There are only 5 sections here, so your test will be on these 5 sections plus 11.6, just the quadratic surface part. So 12.1 is also vector value functions. And what we'll do here, our objectives here, analyze and sketch a space curve given by vector value functions. Okay? We'll extend the concepts of limits and continuity to the vector value functions. Now, I was teaching Cal 1 this morning, and we were doing limits and continuity of single value. Now we're doing vector valued functions. Now, start with the first of those, which is space curves. Okay, so space curves and vector value functions. Now, on a plane, a curve would be any curve like that. Set of ordered pairs, f of t, g of t, together with the defining parametric equations. X would be your f of t, y would be your z of t, because this is your x coordinate, y coordinate. So that makes perfect sense. Where f and g are continuous functions of some independent variable t on the interval I. Interval I are values for t, not x and y, values for t. So you see your x is a dependent variable, and so is your y. Your t is your independent variable. It's not y as a function of x, it's both x and y are functions of t. This definition can be extended naturally to three-dimensional space. A space curve C, as opposed to a planar curve, space curve C, is a set of all the ordered triplets, f of t, y of t, z of t, together with the defining parametric equations, x is equal to f of t, y is equal to g of t, z is equal to h of t, where f, g, and h are continuous functions of t on some interval I. So same type interval we had before of the independent variable t, and these are now dependent variables, x, y, and z, okay, of those functions of t. That's what we're talking about. A new type of function now is called, okay, so back up just a moment. These are called space curves. Okay, space curves, as opposed to a planar curve. Now we're going to jump another rabbit here and go to another kind of function called a vector value function. Rather than being a scalar, x, y, and z, f, g, and h, this is going to deal with vector value function. This type of function maps real numbers onto vectors. Not real numbers onto real numbers, but real numbers onto vectors. The real numbers onto a surface, that's what we were just talking about. This is a vector value function. You're mapping real numbers onto vectors. So here's the definition of vector value function. A function of this form, r of t, is equal to f of t I plus g of t j. These are no longer coordinates of points on the plane or in space. These are now components of vectors in space. This would be in a plane, this would be in space. Or r of t is f of ti plus g of t j, h plus h of t j. Now again, these are just regular scalar functions. These are vector functions, however, the r's. Okay? F, g, and h are scalar functions, but they represent components of a vector as opposed to coordinates of a point. This is vector value function, where the component functions, not coordinate functions, but component functions, f, g, and h, are real valued functions of the parameter t. Vector value functions are sometimes denoted by r of t. This one would be f of t with angle brackets, f of t comma g of t, meaning this is the I component, this is the j component. Or in space, that would be in a plane. In space, r of t would be f of t I, f of t comma g of t comma h of t in angle brackets. This means this is the I component, j component, k component. Make sense? Okay. Technically, a curve in the plane or in space consists of a collection of points and the defining equations. We said that a couple slides ago. Two different curves can have the same graph. Okay? because you've identified the parametric equations differently. The same thing holds for vector value functions. For instance, each of these curves, r of t is equal to sine ti plus cosine tj, and r of t is sine of t squared I, okay, so that's not sine squared, sine of t squared I plus cosine of t squared j. They both draw the unit circle, okay? If you think about this, in terms of your good old trig things, this was the sine of t starts at 0, goes up to 1, down to 0, blah, blah, blah. Down to 0, down to minus 1, okay, it just follows that. So that's what your I components do, and your x component starts at 0, and then, and the y, by the way, is 1, so it's at 0, 1, and that goes down to 1, 0, and then over to 0, minus 1, and then over to minus 1, 0, and just completes the circle. That's going to be the unit circle. That's the graph of it. Well, this one, sine of t squared I plus cosine t squared j, is just the rate at which it's going around there. When this is 0, t is 0 here and here, you start out at 0, 1. Okay? And then when t squared becomes pi halves, this is at 1, and that's at minus 1. But you see, the t squared is going at the same speed, but the thing is, the sine of t, your values that go there, just take it again around the unit circle. It does it sort of strangely, it sort of fits and starts there, but it's still going to trace the same thing. Both of these have unit circles as the graph, but the equations do not represent the same curve, because the circle is traced out in different ways on the graph. This way is circled like this, okay? That one, notice your arguments here are always positive, so you can't possibly go in the negative direction. So it goes, it's going to start slowly and then pick up speed as it goes. This is going to go pretty much same speed all the way around. Okay, but they're traced out in different ways. Okay, not to beat the dead horse. Be sure you see the distinction between the vector value function r and the real value function f, g, and h. All are functions of the real variable t, but r of t is a vector, f, g, and h are real numbers. They're scalar functions. When you put in a t, you get a number out. Put in a t for r, and you get a vector out. The real value factors are sometimes called the real value functions, these f, g, and h. I've been calling them that, called scalar functions to distinguish them from vector value functions, because they have no direction associated, just values. Okay. Goodness, a lot of blah. But this is the first of the chapter. They usually have functions that do this. I mean, slides that do this. Vector value functions serve the dual roles in the representation of curves. Okay, one is by letting the parameter represent time, you can use a vector value function to represent motion along the curve. If t is equal to 3, you're over here. T is equal to 5, you're over there. So that describes the motion if t represents time. Or, in the more general case, you can use a vector value function to trace the graph of a curve, which kind of sounds like the same thing we're talking about, but it's not quite. This is to represent the motion. The other is just to trace the graph of a curve. Okay? Sort of sounds like the same thing, but it's not quite. In either case, the terminal point of the position vector r of t coincides with the point xy or xyz of the curve given by the parametric equations. So this is in a plane. When t is equal to t0, there is where your the terminal point of this vector r is, okay? Then the vector r here at t2, this is at t0, t1 will be here, t2 it'll be here. So the curve that you just described is like this. You usually put an arrow on it to indicate the direction of motion or the direction of development of that curve, okay? In 3 space, and these are much harder to draw and to visualize because some of this is coming out of the board, some of it may be going into the board, but it's all on the board, so you can't really tell what's going on. This looks like a curve that could be a lot like this curve, only this is in 3 space, okay? At r of t1, it appears to be in the xz plane, but you still can't even tell that, okay? This could be back almost in the negative y. You can't tell here, but it looks like it's somewhere pretty close to the xz plane. And then, yeah, you can because it's on the x-axis, this point right here. At r of t1, you're somewhere here, so you're coming out of the plane here, like this, and then at r2, you're at t2, r is over there, and now you're on the y-axis, so you're in the yz plane here. So you come out of the xz plane, come out into the room a little bit to this point, and then you've gone back against that plane, and then it looks like you're going back onto that side of it. This curve C is traced out by the terminal point of the position vector r of t, but this is in 3 dimensions. This one's only in 2 dimensions. This is in the plane, that one's in space. And it's really hard to represent spatially on a 2-dimensional graph. It's just really tough to do, okay? So, and by the way, in both cases, you put an arrow here to show as you progress from T0, T1, T2, which way you're going on the curve. You can only be going one direction on the curve. I say, there are curves that will go back and retrace each other and do back and forth like this. Those are rather bizarre, okay? The arrowhead on the curve indicates the curve's orientation by pointing in the direction of increasing values of t. Unless stated otherwise, the domain of a vector value function r is considered to be the intersection of the domains of the component functions f, g, and h. Now, what do we mean by that? Well, here. For instance, the domain of r here, this is log of ti plus the square root of 1 minus tj plus tk. Okay? Now, what would be the domain of this function? Well, what's the domain of t when you're dealing with f here, log t? Well, the only values t that you can take home with log t. Anyone know? Projector is strobing some on me and it drives my eyes crazy. What's the domain of log t? Anyone know? Give a guess. Second? Close, okay? As long as when you set that 0, you put a parenthesis in front of it. It doesn't count 0. It's all positive values. You don't count 0. You can't take the log of 0. You can't take the log of a negative number. You can take the log of any positive number. Okay? So the domain of this is t is greater than 0. Not greater than or equal to, greater than 0. Okay, how about here? Square root function. What term? Second? What's it? Yeah, it can't be negative. This thing in here cannot be negative. So 1 minus t, here's one way to write this. let me get my pen set up. Okay, 1 minus t has to be greater than or equal to 0, right? Can't be negative, okay? But you can't take the square root of a negative number, okay? Here, t has to be greater than 0. Here, 1 minus t has to be greater than 0. Well, what you can do with that, and there's either one of two ways you could do it, I kind of like this way, adding t to both sides, and that gives you 1 is greater than or equal to t. In other words, t is less than or equal to 1. Okay? Now how about this one? What's the limitations on t there? All real numbers, no limitation at all. All real numbers. But all these can't be true. Okay? This says t has to be greater than 0. This says that t has to be less than or equal to 1. That says t could be anything. Well, you limit it to the most limiting factor. It has to be greater than 0, less than or equal to 1. So your domain for this function, this vector value function, can only be the domain of this function, r. That r right there would be, I'm going to write it in interval notation, 0 to 1 bracket. That's all, folks. You can't go anything negative, or else this isn't defined. You can't go anything greater than 1, or this isn't defined. So it doesn't matter what the t can do with the k, you've got to be limited to those values. So there's your domain of this function. From 0 to 1. Counting the 1, not counting the 0. Make sense? Okay. All right. So here's example 2. I don't think we did example 1, did we? So let's go back. I'm not going to find a place to do example 1. So we'll do example 1 first, and then we'll come back and do example 2. Example 1. I must be going to have company. My nose is itching like crazy. Okay. R of t. Now, I can't write bold. The book writes bold, and the slides write bold. I can't write bold. So if I'm doing a vector, I put an arrow over it. Okay? R is a function of scalar t. T is not a vector. T is a scalar number. But R is a vector. R of t is equal to 2 cosine t I minus 3 sine t j. Oh, that's all. And this is good. 0, excuse me, less than or equal to t, less than or equal to 2 pi. Okay. So sorry. I'm just running out of energy. Okay. Now this is a planar vector function, so we can represent that on this two-dimensional plane. Okay. So we'll do 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5, 6. 1, 2, 3, 1, 2, 3. Okay. Hopefully that'll cover most of what we need. All right. Now, this is the xy plane, so don't get confused. This is the x plane, this is the y axis. You don't have a t-axis on here, okay? We pick a value t, find the functions, and plot them here. So give me a t. Second? Okay. 2. Okay? T equal 2 is certainly in the domain here, so we can choose that. So t equal 2. I don't know what cosine of 2 is, do you? You can plug it in your calculator if you wanted to. I like to do with things I can calculate fairly exactly. Say again? Okay, that certainly would be a good one. I like that better. 1, 2, those are going to be hard. Pi over 2 I can do. Okay, what is cosine of pi over 2? 0. So this will be a 0i. And what's sine of pi over 2? 1. So minus 3 times 1 would be minus 3. So it's going to be down here. So 0 on x minus 3 on y. There's that point. So this is t equal pi halves. Okay? Give me another t. Pi. Okay, we'll do pi. Cosine of pi is? -1. So it'll be a -2 for your I. And then, second? Let's see, what did you say? Pi? Yeah, that would be 0. So, what did I say? -2. Okay. So there, that one is. So we know we're doing something about moving from here to there. Okay, because we're going in that direction. Give me another t. 2 pi, that's perfectly fine. That's counted here. When t is 2 pi, what is cosine of 2 pi? 1. So 2 times 1 is 2, so the x-coordinate is 2. And I'm sorry? I can't hear. Did you want to do 3 pi over 2 first? We could, but we don't have to. What do you get? This would be minus, wait, what did I say? No, 2 pi, that would be 2, and this would be, second? 0, okay? So 2 for x and 0 for y. Okay, there we have, this is t equal pi, not a line under it. Having trouble reading, my cataract has given me some issues, and this will be t equal 2 pi. Now, by the way, when t is 2 pi, what's it the same as? When t is equal to sines and cosines? The period is 2 pi. So time plugging in a 2 pi here is also going to be like plugging in a 0 there, because it's the same value. So this is, not only is this t equal 2 pi, this is also t is equal to 0. Now, did you want to do 3 halves pi?
I have a question. Why is it going in the direction of
What?
clockwise instead of counterclockwise?
Okay, it's because a couple of reasons. You're leading off with cosine rather than sine. Usually cosine is associated with j and sine's associated with, I'm sorry, I said it backwards. That's right, but this is a minus sign here, so that has us going the other direction. But if we did it, we would be right up here. So what we have, it starts here and goes through there, goes through there, goes through there, and goes through here. This would be an ellipse, and it's going in this direction. You don't need but one arrow, but I've got it. And that makes one complete one complete path around the ellipse, and you got it. So that would be, what did they ask for? Sketch the plane curve represented, and we just did. That's an ellipse. And you see, cosine starts at 1, so to speak, you're doubling it here, and then does this and this, you know, back and forth like this. Okay? Sine would normally go like this and that, but because it's minus sine, it comes down and then back up again, down and back up. So it's doing this. Most of it because of that minus sign right there. That's why it goes clockwise over it. Now that's supposed to be more elliptical. My has this end be too pointed and that would be too rounded. You get the general idea. Okay? See it? and if you look in your book, you'll see a shape fairly close to this one. Not exactly, okay, but fairly. All right, that was example 1. I may have to go get some more caffeine because my head is going nuts on me. But let's see, we've only been at it a little over an hour, so let's go at least another half hour, and maybe we'll take a quick break. All right, now we'll do example 2. Sketch the space curve represented by the vectored value function r of t is equal to 4 cosine t plus 4 sine t plus, 4 cosine ti plus 4 sine tj plus tk. And this is good for 0 is less than or equal to t is less than or equal to 2 pi. Okay. Gracious, my eyes hurt. I think all this strobing that it's done is just from the very first class. It was starting giving me problems, and now it's not quite like a migraine coming on, but it's close enough. All right. Now, by the way, I think I mentioned this early in the term. Okay. We're still very early in the term. This is one of those examples that says, see larsoncalculus.com for an interactive version of this type of example. So even if you don't have a book, you can go to larsoncalculus.com and see them talk about, hear them describe this very problem. So if you got your other book you're using, like one from your home campus, you can combine that, but you can actually see what we're talking about here at larsoncalculus.com. Okay, and here is the function here, and now we're going from 0 to, strange here, isn't it? 4 cosine ti plus 4 sine tj plus tk. In the book, it's going to 4 pi, and on the slide set, it's only doing 2 pi. So I'm going to put 4 pi up here as well. We'll do 2 pi first, and then see what happens if we do 4 pi. Interesting. I hadn't noticed that. Okay? So, unfortunately, we got to draw some coordinates. Okay? And this is 3-dimensional. So again, we're going to be trying to plot a 3-dimensional shape on a 2-dimensional board. It's not going to be pretty, I don't think. So let's give it our best shot here. Whoa, I don't want that. Okay. No. Okay, let's try that again. Whew. Okay, this is our X, this is our Y, this is our Z. Now this isn't the best orientation to do a graphic because things come out weird shaped on this, but it's the easiest thing for me to set up and go from. Okay? Now, just looking at what we've got here, I know, sorry. Okay. 1, 2, 3, 4. Okay. We're not going to need this many. Sorry. X, negative X is going back this way, and we'll need 1, 2, 3, 4 going back here. That's all we need. Y, 1, 2, 3, 4. Negative Y going back this way. 1, 2, 3, 4. Here's where the problem child comes. I'm going to have to suppress this a little bit. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7. We probably can't get everything there, but let's do our best. Okay. Give me some place to start. Give me a T. Give me a T. Anybody? Second, pi? Okay, now, you did this to me last time, and we had to backtrack and do, why don't we start at the lowest T and go up to the highest T? So that way we'll get our direction as we go. So let's start with T equals 0. So I say, give me a T, I'll tell you which T. That T, okay. T equals 0, what will that be? Say again? Well, no. The book has us going to 4 pi. The slide only has us going 2 pi. So let's do the slide first, and then we'll see what happens if we go on to 4 pi. I don't think we'll be able to plot it on here, but we'll give it a shot. So let's start with T equals 0. They both started there, T equals 0. What's your x coordinate at T equals 0? 4. So that would be 1, 2, 3, 4. So here's where we're starting. Okay? And that's the x coordinate. Y when t is equal to 0 is 0. So we're still right there on the x-axis. Z when t is equal to 0 is 0 also. So this is exactly where we are. This is our starting point. T is equal to 0, right there. 4. 4, 0, 0. All right, let's go to pi over 2. That's how I like to think too. What is cosine of pi over 2? Okay, that's 0. So x is going to go back to 0. Okay. What is sine at pi over 2? 1. So this is going to be at 4. So y is going to be 4, 1, 2, 3, 4. So that, we'll hold this one now. But what's your z? Pi over 2. Well, pi is about 3, so it's about 3 halves. So it goes up about 1.5. So I scaled a little differently here because I knew we were going to use more. So it's going there. So it started here and comes out a bit and goes to there, okay? And it's going in this direction. It's curved, and that should be a quarter of a circle when plotted down onto the XY plane, but it's coming off the XY plane. As you increase in t, this is coming off the XY plane on z. So I can't draw this well, okay? Okay, what's next? Pi. Cosine of pi is -1, so it's -1 on x, which will be a -4 on x. Second? 0. So the y is going to be 0, so we're back there, except we're pi, which is about a little up more than 3 up. So we would have been right here on this spot here, but now we go 3 up, which would be, trying to get the scale right, 1, 2, 3. So somewhere about here. So you go out to there and then back to this one. Now you're coming up as you're doing this and coming around, okay? Still going in that direction. What's the next one? 3 pi over 2. And cosine of 3 pi over 2 is what?
0.
0. So the x is going to be 0. Sine of 3 pi over 2 is -1. So the y is going to be -4, which would be back. Boy, here I've done it again. And this is how I destroy computers. Somehow my chair got over the cord. I've poured the computer off the desk before, and that's been tragic. Okay, so this is 0 on x, no, yeah, 0 on x, -4 on y, which is back here, except now, what's our k? 3 pi over 2. Okay? Now pi is about 3, and 3 times a little over 3. Let's just call it 10 over 2. It's going to be about 5 up. Okay? So that's going to be 1, 2, 3, 4, 5. Okay? 2, 3, 4, 5. Somewhere right about here. Now the thing is, this thing is still climbing, though it looks like it's going down some. It's not. It's still climbing. It's just that this is closer to us. It's so hard to represent this well. And then what would be when t is equal to 2 pi? Okay, you're back to right here, only now you go up. It's 0, it's 4, 0, but now you're up to 2 pi is about 6.2, 6 1/4. Okay, so you go up from here, 1, 2, 3, 4, 5, 6 1/4. So it's coming around to here, and this should be directly over that one. And now if you kept going, you would be, over this one, and then over this one, then you'd be off scale somewhere up here, and then come back to around here, and then you'd come back another 6 up here. So it's really tough to see. You'd just be 2 spirals. So what we have now is a slinky. Okay, you can think of that. It's actually called a helix, and you're going around and going up as you go. It's tracing out a circle of radius 4. That's what this is doing on the XY plane, but it's going up as you go and just climbing. Does that make sense? Okay. Now, if I could have drawn, well, let's see. Oh, yeah, I think it'll show it here. So let me clear my mess out of the way and let you see how they did it. From the first 2 parametric equations, x equal 4 cosine t, y is equal 4 sine t, you can obtain, if you squared both of those, you get 16 cosine squared t plus 16 sine squared t. That would be x squared plus y squared is equal to 16. Okay? Circle of radius 4. The curve lies on the right circular cylinder of radius 4, centered about the z-axis, and then it goes up the cylinder as it's going. So that's what it looks like, and that's what I was trying to draw. You see, they've oriented their XY a little differently from mine, so theirs look a little bit more like it. But you see, this is still climbing, even though it looks like it's pointed. It really isn't. This is on the back side of the cylinder, coming around to the front side of the cylinder, the back side of the cylinder, the front side of the cylinder. So it keeps going. So this is going up to 4 pi. That's what I was trying to illustrate. Ours, okay. Sorry about this. So evidently they did the 4 pi too, so that meant they really meant this to be just like was in the book. That should have been to 4 pi, not just to 2 pi. No, I'm sorry, I said it wrong. Now I'm totally confused. Okay, yeah. The book had the 4 pi. That's what this was supposed to have been. That should have been a 4 pi because they show this to 4 pi. See, one time around to here would be 2 pi. This gets you up to 4 pi. So this is what the book was calling for. Okay. And you see it just keeps on climbing. Stays on that right circular cylinder and just keeps on climbing up. Spiraling upward. It's a helix is the name of that. There's the name of it there. Okay. And it's bolded in the book too. Now, in examples 1 and 2, you are given a vector-valued function asked to sketch the corresponding curve. The next 2 examples address the reverse problem, finding the vector value function to represent a given graph. Of course, when the graph is described parametrically, representation by the vector value function is straightforward. When the graph is represented parametrically, like we've had here, for instance, to represent, now this is a new one here, and let's see. No. have, oh. I guess I should have done this first. Here's a real-life example of a helix shown in the drawing here. And this actually is a double helix. Anyone know what this represents? DNA. And this is how it's done. The pairs here are in certain things that connect certain pieces of that too. And these are equal distance apart. Just, again, it's hard to represent a three-dimensional structure on a two-dimensional board. These are just about right. These are the same length. It looks shorter. That really looks short. That looks incredibly short. Then they start getting longer again. These are the actual lengths here, that one and that one. And then they get, because you're twisting back around and twisting around. So this is your DNA. And what is it? 23 pairs makes up every human being. 23 and me. Okay. So 46 entities there. You know, one at either end of the thing, and that's, I guess those are called the genes, are they? Whatever. And then you have a wide variety of what they can be. So anyway, this is your double helix. And that will determine hair color, height, weight. I mean, just about everything there is about you is determined by that sequence that we have there. All right. Now, before we get to this part, like they were saying, what if you had this as a vector? R of t, I can't draw bold, so I have to put an arrow over it, is equal to 2 minus t I. Oh, I meant to say this too. I'll say it as soon as I finish writing. I'll forget it by then too, but I'll try it. 3tj plus 4 minus tk. Now, if you've noticed what I'm doing here, some vectors I just put an arrow over it, and other vectors I put a housetop over it. Or that's also called something else. What's that called? Whatever that symbol is. Okay? Why? Anyone got an idea? I can't draw a bulb. The book, because of that bulb, that bulb, that bulb, that bulb. You just tell they're all vectors. Why I put the housetop, this indicates that's a unit vector. That's a unit vector. That's a unit vector. This one's not necessarily a unit vector. So all unit vectors I try to put the housetop on, because that to me, it plants it in my brain, these are unit vectors. Okay. Now, let's do a drawing of that one. I think is what they're going to have us do. Okay. Won't be able to come out too far here, but we'll do a few places. Okay. Give me a t. Let's start at 0. Okay. All right. 0. What would you have? 2i. This is x, y, z. So 2i, 0j, second, plus 4k. So 4k would be 1, 2, 3, 4 up there. So go up 1, 2, 3, 4. Okay, so here's our starting point. This is t equals 0. Okay, let's go to 1. What would be your next? T equal 1. 1i plus 3j, okay, plus 3k. So that would be Wait, no, it's here. Okay. All right, here's the next point. So it's going from there, and this is, I'm going to put straight lines because this isn't second power, this is first power. Okay. And give me another one. T equal 2. That would be 0i. So we're going to be 0 on the x-axis. Okay. YZ plane. Plus 6j. Okay. Somewhere out there. And I can't remember what I'm doing. Yeah, 2. That would be 2k. Okay, so we're right here. If I could draw a straight line, that looks like that's heading in a straight line form. Let's do 3 just to see. That would be minus 1 I, which would be back here. 9j, even further out there, and 1k. So yeah, I think this is, and if you went here, so this is going to be a straight line. I can't draw straight lines too well with 3 space, but it's coming out here, going in there. That's where it crosses the YZ plane, and then it's going back that way, like that. So that is a straight line. So everything boils down to your parametric equations. Okay. So let me see if we can do, I think I'll go back to here and do example 3. Represent the parabola y is equal to x squared plus 1 by a vector value function. So now we're going the other way. So how could we represent that by a vector value function? Let me suggest the easiest way. Find the most complicated variable. Which would that be? What are you doing the most to? Okay, the x, right? So let's let x equal t. Then, guess what y will be? If x is t, what's your y? Plug in what x is. T squared plus 1. There it is. So here's your vector value function. R of t is equal to ti plus t squared plus 1j. That's it. That's the easiest way to go on one like that. Okay? There you've represented that. There's tons of other vector functions you could use to represent that. Give me another thing for x. Just make up anything with t in it. Three halves t plus 7. Then go to x equal 3 halves t plus 7. Then plug that in here and figure out what the y is, and that'll be your y. Ew, who wants to do that? Keep it simple, okay? So the simplest is just let x be t, the most complicated thing here, and then y, just plug that in. You can always do that. So it's really easy, most of the time, to go this way, okay? Now, if you had chosen x equal minus t, oh, and by the way, both of those will form a parabola. And the parabola is located at the vertex here, and it goes like this, okay? Now when we chose t equals 0, that puts the x of 0 here, and y is 1. Okay? T is equal to 1, you'd be going this way. So this would be going in that direction. If you chose t equal -1, then it would have been going this way. What color you want -1 to be? Second? Red? Okay. We'll make it red. -1, this is t equal -1, and this is t equal 1 that way. Okay. Both starting at the same place, they just go in different directions. So then negative t's would have been over here, going down to 0 and here. Here your negative t's are here, going down and going like this. So. All right. Now, let's do example 4. So I'm going to erase this. This is pretty exciting stuff, isn't it? Oh yeah, okay. Example 4. Sketch the space curve C represented by the intersection of the semi-ellipsoid x squared over 12. We didn't know we were going to be doing these so quickly, did we? Plus y squared over 24 plus z squared over 4 is equal to 1. And what we have is z has to be greater than or equal to 0. That's what makes it a semi-ellipsoid. If they hadn't said this, that would have been an ellipsoid. But if you require z to be greater than or equal to 0, then this is the ellipsoid only going up. It's not going down here. Okay? So, sketch the space curve C represented by the intersection of that semi-ellipsoid and the parabolic, cylinder y is equal to x squared. Okay. Says sketch the space curve represented by the intersection of that semi-ellipsoid and the parabolic cylinder y is equal to x squared. Then find the vector value function to represent that graph. So let's first do the graph. I just thoroughly enjoy doing this, don't you? Okay, this is your x, your y, and your z. All right. I don't think we did enough of the graphing of this. Evidently, they don't think so either. We don't need any negative z, so I'm not going to draw it down there. Okay? Now, okay. How I'm going to begin this is we'll assume x and y are both 0. So we're going to be on the z-axis. And z's obviously going to have to be 2, right? So if x and y is 0, z has to be 2. So that means at the origin here, z has to be 2. So right there is 1 point. Okay? Now, let's do something else sort of bizarre here. Let's choose y and z both 0. So now we're on the x-axis. So x must be the square root of 12, right? Okay? The square root of 12 is 2 times root 3, right? Okay. Root 3 is about 1.72. That is about 5. So this will be something 1, 2, 3, 4, 5. Okay? Now, y and z, x and z can both, x and y can both be negative, so you also have a other point back here, okay? Yeah. All right. Now, let's choose the point where so these are two intersection points there, one there. Let's pick where x and z are both zeros, and then what must the y be? Yeah, where x and z are both zero, what would your y be? Yeah. This thing has to equal 1, so what must y be? Square root of 24, right? Well, that would be 2 times the square root of 6, right? Square root of 24. Okay, square root of 6 is something greater than 2, less than 3. So 2 times something has to be, this should have been something around 3 or 4, between 3 and 4, because I said square root of 3. So I did this one a little too far. That should have been something a little around 3. So let me take these off, and this will be here and there. Plus or minus there, somewhere, not up to 5. This one was the one I was thinking of. This is to 5. 1, 2, 3, 4, close to 5, because square root of 25 would be 5, so you're just a little bit short. So maybe about right there and right there. Okay, so let me take these two off if I can get away with it. There, I got that one gone. I got that one going. Okay. So, here's how I draw it. On the XY plane, it's a minor axis here, major axis here, minor axis here, major axis. That's supposed to be an ellipse. It's pretty ugly, isn't it? Don't answer that question. Nope, wrong. Yuck. Get the wrong icon down here. Let me get that out of there and try it one more time. Something like that. It's supposed to be an ellipse. On the XZ plane, the ellipse goes like this, and on the YZ plane, the ellipse goes like this. So that's our ellipsoid. It's sort of like, if you can try to imagine this to be a little bit better shape here, it's like maybe you're baking a loaf of bread and flatten the pan and sort of that ellipsoid shape on top of it. My drawing really stinks, okay? But that's the semi-ellipsoid, okay? Now what we have is a parabolic cylinder, y is equal to x squared. Well, y is equal to x squared is going to open across the y, and so that's going to be at 1, 1, at minus 1, 1, and then 2, 4, and minus 2, 4. My graph is really pretty pathetic, but this is the parabola there, and it's going to come up and intersect this thing here, so something like that. It's going to be a lot weirder than that. In fact, let me show you how weird it is. Okay. There's your semi-ellipsoid here. Now, they did show the back half of it. Well, the reason is it's not going to intersect that anywhere. So this is going to come up, climb up the ellipsoid, go up to here, and then climb back down there. So this is how it looks, okay? And we have to come up with an equation that describes this curve that we have right here. Okay? That doesn't look like a lot of fun to me. Okay? But the points that it touches, we know that it touches here, which is 0, 0, 2. We knew that one. And the one down here, goodness, my nose itches. Let's see if I can figure out why that is at 2, 4, 0. Well, here's what you do. You know this has to be true, and it has to be true on that too. So instead of y, we're going to put in x squared. So this will be x squared over 12 plus x to the fourth. X squared times x squared is x to the fourth over 24 plus z squared over 4 is equal to 1. So that's going to be the equation of this curve. And as we said before, oh yeah, there it is. So let's combine these two together. And what we have here, goodness gracious, this is a terrible feeling. Let's multiply everything by 24. So this will be 2x squared plus x to the fourth plus 6x, z squared is equal to 24. Okay? Now, let's complete the square of this one. This will be x to the fourth plus 2x squared plus 6z squared equal 24. Okay? Complete the square here, and that would be plus 1, because half of 2 is 1. Okay? But we just added 1 here, so make that 25. So this will be x plus 1, x squared plus 1 squared plus 6z squared is equal to 25. So when z is equal to 0 here, that's this point down here, when z is equal to 0, then you have x squared plus 1 squared is equal to 25. Take a square root of both sides of that, you get x squared plus 1 is equal to 5. So x squared is equal to 4. So x is equal to plus or minus 2. So that's why it's x is plus 2 here, minus 2 here. Well, then plug that into here. That would be y is equal to 4 and 4. So that's why this point down here is indeed 2, 4, 0. Over here is minus 2, 4, and 0. Yeah. So they did pick those out right, but you had a bit of doing to get why that's true. Now maybe there was an easier way to do it, but that's the only way I could figure out real quickly. So I know that point's true and the point up there is true. Okay? Now, what we have to do is come up with a parametric equation that gives you that. And this is the function. Actually, I think I would go back to any reason not to use this one. But you can always figure out what the y value is once we have x's. So we did, like we said before, let x equal t. Let's see what happens there. Okay. We know from this that y is equal to t squared. Okay? And then we know from that, if we do this, that would be t squared over 12 plus t4 over 24 plus z squared over 4 is equal to 1. Okay? And let's solve for z then. So we'll subtract t squared over 12, subtract, I can't read my own writing, I think that's a t, not a 6. It's a t4 minus t4 over 24. And that's equal to 1. Okay. No, this is a z squared here. No, I'm sorry. I've gotten all crossed up. I've written these things too close to each other, so let me spread them out a little bit. Okay. It's getting late in the day and I haven't eaten, so I'm so hungry. Okay, we're going to subtract these from both sides. So you have z squared over 4 is equal to 1 minus t squared over 12 minus t to the 4th over 24. Right. And then multiply everything by 4. And that will make a 3 down here and a 6 here. Okay. So now we have z squared is equal to 4 minus t squared over 3 minus t 4th over 6. And then the z is plus or minus the square root of those. Except z is never minus, so it's going to be positive the square root of 4 minus t squared over 3 minus t4 over 6. It's ugly there, but there. So there's what your z is. So here's your parametric equal one set. Now this isn't the best set probably. X equal t, y is equal to t squared. You know that has to be true because that's true. And then z is equal to the square root of t, blah, 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 blah. Okay? Now, so let me write that down with these two. Z is equal to the square root 4 minus t squared over 3, I believe it is, minus t 4th over 6. Okay, now that's not a very pretty z, but it works. They did the first two the same way. They did their last one really bizarrely. And I can't say for sure why they did it that way. That works just as well. I think you can multiply theirs out and see if you get the same thing. I think you do. They put all this over 6, I believe. Yeah, all over 6, so that would make this 24 minus 2t squared, and then factor the numerator. I don't know why they go to that much trouble. That works just as well. Okay. So, I don't know about you. These are not straightforward, okay? But follow what they tell you, okay? And you can make them work. I can't draw the picture worth of 2, but you can do the math on it, okay? So, as we saw before, once you get everything together like this, okay, obviously the most complicated thing is the x. Let that be your t. And then from this, that you know this has to be true, y is equal to x squared, then y is equal to t squared. Oh, it's x squared, t squared. Then you put those in for your x's and y's here, and then solve for z, and that gives you the z we just came up with. Okay. So that's the procedure. Not pretty, but doable. Now, any questions on that? I know that's a lot of blah, blah, blah. Okay, let's move to limits and continuity. Okay. Here first is the definition. They do some other stuff first, but here's the definition. How we're doing on time. Okay. What is it now? About 4:20 or so. Y'all need a break? I know you've been sitting very patiently for a while. Are you okay? You want to take a break? Okay. I don't need one, but I know I'm tired. I would need to go get a little swig of caffeine and sugar or something. So all right, so here's our definition of continuity for vector value functions. If you remember, continuity to me was not really all my favorite of definitions, but here's what it means. If R is some vector, bold R means a vector value function, such that R of t is some f of ti plus g of tj. If it was 3 dimensional, this is in a plane in space, you'd have a k. Then the limit as t approaches some value a of r of t would be the limit as t approaches a of the f of ti plus the limit of as t approaches a of the g of tj, provided that f and g have limits as t approach a. If both of them do, then that's what the limit is. Okay? So it's just plug it in, plug it in. If the limit exists, then your function exists. If it's vector value function such that r of t is f of ti plus g of tj plus h of tk, then the limit as t approaches a of r of t would be the limit as t approaches a of f of ti, g of tj, h of tj, k, and provided those limits exist, if each of those exists, then the limit has a function as t approaches a. So it's a pretty straightforward thing. Basically, you plug it in, plug it in. See what happens if you plug. If you wind up getting something undefined here or wherever, then the limit doesn't exist. It's going to blow up somewhere. Okay? Or possibly have a hole in the function or something like that. But most of the time, no, if the limits exist, it will have that for a hole in the function. It's only if it's blowing up, going to positive or negative infinity in one of those areas, then the whole thing falls apart. Okay? So, if r of t approaches the vector L, remember now we're no longer dealing with scalars, we're dealing with vectors. So if r is a vector, L has to be a vector. That's the limit of that vector. As t approaches a, then the length of the vector r of t minus L approaches 0. That means that the magnitude of this as that gets closer to 0 as t gets closer to a. Okay, now what does that mean? If this is the limit for the function r of t, here's your origin there, and here's the r of t, here's your limit L. As t is approaching a, the vector r of t is coming closer and closer to this vector L, and if that's going to 0, as t approaches a, that means the limit exists. Okay? So here is some r of t. This is some r of t closer to a, r of t closer to a. There's an r of t at a. Yeah, so that limit does exist. And it doesn't blow up and go to an infinity or something else like that. So as t approaches a, r of t approaches the limit L, vector L. For the limit L to exist, it is not necessary that r of a be defined or that r of a be equal to L. They just need to approach it. Okay? R of t may not even be defined. There may be a hole in the graph there, so it may not be defined there, but it just needs to approach it. All right, the next definition extends the notion of continuity to vector value functions. Thought we were just doing that. Okay? A vector value function R is continuous at a point given by t equal a when the limit of R of t exists as t approaches a. So number one, the limit of R of t must exist. Before we said it didn't have to, now we say it does. So the limit as t approaches a of R of t would be R of a. That must be true. The vector value function R is continuous on an open interval I when it's continuous at every point in that open interval I. Again, the interval I is of values for t. From t equal this to t equal that, that would be your interval I. Okay. Hopefully it's just what you would expect. So let's discuss the continuity of the vector value function R of t is equal to ti plus aj plus a minus t k, where a is just some constant, at t equals 0. What is the continuity of this vector value function there? Okay? At t equals 0. What would be the value of that? When t is equal to 0. Plug in a t equals 0. What would we get? 0i, so no component in the I direction. Plus aj, because a is just a constant, so a on the y direction. Plus a, yeah, but t is that going to 0, that would be a squared k. So you would be this vector valued function at t equals 0 would be r of 0 would be 0i plus aj plus a squared k. That would be the function, the value of that vector value function there. All dependent on a, nothing else. Okay? So as t approaches 0, this would be the limit of that, that would be 0. Limit of that, that would be a. Limit of that, that would be a squared. So plug it in, 0i plus, you could just leave that off if you wanted to, aj plus a squared k. That would be the limit of this vector as t approaches 0. Does that make sense? First thing you try is just plugging in. Okay? If you get something that never could be true, 17 over 0, never going to happen, then the limit doesn't exist. The square root of -3, that doesn't exist, so that limit wouldn't exist. Log of -14, that doesn't exist, so those would not exist. But if you get anything that does exist, that would be it then. Now, the ambiguity comes if you got a 0 over 0, the indeterminate case, then you have to do some figuring on that to see if the limit really does exist. But in general, just plug it in and see. Okay, so aj plus a squared k. All right, because r of 0 is that, you can conclude that r is continuous at t equals 0. There's no problems there. For any value a, everything's defined. Okay. By similar reasoning, you can conclude that the vector value function r is continuous at all real values of t. Okay. So let's go back and look at the function again. There it is. Okay. This is a good old polynomial. That's a good old constant, okay? And that's a good old polynomial. Good everywhere. There's no place where any of those get into trouble as t approaches any value, okay? If one of those was a log function, a square root function, or a rational function, you may have problems. Other than that, you're fine. Okay, trig functions, you couldn't have places where those trig functions are not defined. Sine and cosine, defined everywhere. Okay. For each value of A, the curve represents the vector value function in example 5. So, okay, this function here. For each value of A, the curve represented by this vector value function in example 5 would be a parabola. Okay, because you see the J here, the Y component is a constant. It never changes. So there's no T dependence here at all. So this would be dependent on X and Z only. So these are all parabolas in the XZ plane. The Y's are constant. Okay? So in the XZ plane, there's a parabola, there's a parabola, there's a parabola, there's a parabola, there's a parabola. That's basically a parabolic hyperboloid. Okay? That looks like the shape there. Okay? Because that's a parabola in every dimension. And in the XZ plane, however you cut it, it always forms a parabola. Okay? So that is indeed a hyperbolic parabola. You think of each parabola as the intersection of the vertical plane, the hyperbolic paraboloid. Let's see if we can get this. Okay? Again, find the, let's see, sort of doing this in the other direction. Your X equal T, Y is equal to A, and Z would be Y squared minus X squared. Y squared minus X squared is Z. Okay? Yeah, Z. That's it right there. So there is the hyperbolic paraboloid. Hyperbola here, single value here, so if either of these are constant, those are both parabolas. Okay? So, yep, hyperbolic paraboloid. So we are using our quadric surfaces quite a bit in this first part. Whoops. Okay. That was example 5, and we just did that one. They don't do example 6, so let's go back and do example 6. See if I can get any better than that. It might give me a little more white space here. So let's do example 6. Determine the intervals on which the vectored value function R of t is equal to ti plus the square root of t plus 1 j plus t squared plus 1 k is continuous. Okay? Determine the intervals on which that vector value function is continuous. Are there any problem children in our mix here? Which? What? The square root. This is a good old polynomial, good everywhere. This is a good old polynomial, good everywhere. Square root is not good everywhere. What has to be true about it? The argument has to be greater than or equal to 0, right? It can't be negative. So how do we say that? T plus 1 is greater than or equal to 0. Has to be positive, cannot be negative. Okay? So that means T, if you subtract 1 from both sides, T is greater than or equal to minus 1. That's all you have to say. So determine the intervals on which the vector value function is continuous. That's it. This vector value function, RT, continuous for all t greater than or equal to minus 1. Otherwise not. This didn't care, that didn't care, but they're good for all values greater than or equal to 5. Okay? So the interval would be from -1 to positive infinity. Okay? That's how they like to write their intervals. That to me says it just as well, but they like to do it in interval notation. So it's -1 with a bracket on it because of the equal sign there, up to one as high as you want to go. Any t there. That finished 12.1. Okay, homework exercises here. Any of the odds, 3 through 9, they're all at Calc Chat. 3's at Calc View. Do number 11, it's at Calc Chat and Calc View. Do either 13 or 15, they're both at Calc Chat. Do 17, it's at Calc Chat. That's a sort of think about it problem. Matching, I would do all of 19 through 22. Now, only the answers for the odds are in the back and at Calc Chat, but you should be able to match them all up, okay? You just won't be able to check them, okay? Then do any of the odds 23 to 29. They're all at Calc Chat. 25's at Calc View. Do any of the odds 31 to 37. They're all at Calc Chat. 31's at Calc View. Try to do number 39. They say you might need a computer algebra system to graph it. See if you can sort of get a general idea on your own. If you got that, use it, but if not, don't sweat it. Try to do 41, same deal. They say you might need a computer algebra system to do that graph, but see what you can figure out on your own. Then do any of the odds 43 to 45, either one of those, are both at Calc Chat. And by the way, so are 39 and 41. Then do any of the odds 47 to 53, they're all at Calc Chat. 51's at Calc View. Do any of the odds 55 to 61, they're all at Calc Chat. 55's at Calc View. Try to do 63, it's at Calc Chat. Any of the odds 65 through 69, they're all at Calc Chat. 67's at Calc View. And any of the odds 71 to 75, they're all at Calc Chat. 71's at Calc View. There's exploring concepts. You could try either 77 or 79, or just check with Calc Chat. They should both be there. Then 81 is an interesting looking staircase. You can play with that if you'd like. That's at Calc Chat. Then there's a couple of proofs, 83 and or 85. They should be at Calc Chat. Now, all of you pre-engineering majors, or any of you math majors? Engineering? Okay. You can do the proofs if you'd like. I don't think engineering is going to require those, but if you do, you can. Math majors probably need to think through the proofs. Okay, 87 is the think about problem. You can think about doing it if you want to. There's a particle motion problem, 89. And then there's a section project here. Usually I don't say much about it, but this is talking about the witch of Agnesi, which is a misnomer. It's just a curve. But they called it a witch because somebody, in translating from Latin to some other language, missed the translation, and where it was supposed to be something like a curve or a shape or something like that, the translation come out witch, okay? Which is very inconvenient because Agnesi was a woman. She was one of the very few early, well-recognized, famous great mathematicians who was female. Most of the time, women couldn't even have education. She managed to get it. I think her dad was a professor or something. She managed to get an education. She was brilliant in mathematics. And she came up with this curve, and then they wound up calling it the Witch of Egnacy. And you can't convince me it wasn't partially because she was female that they would call it a witch, but I don't know. But you can write on her how she came up with the curve or who uses this, okay? But that's another possibility. So let's move on to, yes. No, these are only for your practice because the tests are going to be similar to them. Now, if you find yourself hitting the same brick wall and you don't know why, you can turn them in to me and say, what am I doing wrong here? Okay? But you see, you've got the answers in the back. You've got the odd number exercises worked out at calcchat.com, and then you have some of them worked out at CalcView, which give you even more. So, hopefully you can get it, but if you still can't see where you're making your mistake, turn them in, and we'll work through it together, see if we can figure out where the mistakes are arising. I think you'll probably be able to figure them out, but if not, we'll do it together. Okay. Does that answer your question?
Yes.
Yeah, okay. Yeah, these are strictly for your benefit, so when it comes test time, you're not, oh, how in the world do you do this? You've already been practicing how you did that. All right, let's move on to 12.2. How are we doing on time? Oh, we got about half an hour. Good. Okay. 12.2, we'll start from sample slide, current slide. We're still in vector value functions, and 12.2 are going to be talking about differentiation and integration of vector value function, which to me is much easier, much more straightforward, just hopefully what you expect it to be. Okay? We'll differentiate vector value functions, and we'll integrate vector value functions. Okay? So let's start with differentiation. Here it's going to blinking and strobing again, which drives my head crazy. So, the definition of derivative of vector value function parallels that for real value functions. Here's what it is. Definition of derivative, vector value function. Derivative of a function, derivative of a vector value function R is R prime of t. Now what that means is derivative of R with respect to t. That's the independent variable. That's the limit as delta t approaches 0 of R at t plus delta t minus R of t divided by delta t, which is exactly what our old definition of a limit was if these had been f's there rather than r's. Just the same. For all t in which the limit exists, if r prime does exist, then r is differentiable at t. If r prime exists for all t in an open interval I, then r is said to be differentiable of that interval I. And differentiability of a vector value function can be extended to closed intervals by considering one-sided limits. Just like we did, hopefully you did, back when you did derivatives, definitions of derivatives. Okay? Everybody got it? Okay. Differentiation of vector value functions can be done on a component by component basis. This is what makes it pretty easy. You just, the x, y, and z, I, j, and k don't depend on each other at all. They're independent of each other. So if you're differentiating the function, differentiate that, and then differentiate that, but keep it with the I, keep it with the j. So applying the definition of derivative produces the following. Now this is the long roundabout way of doing it. Okay, first, r prime of t, as we just saw, was the limit delta t approaches 0, r of t plus delta t minus r of t over delta t. That was from the previous slide. Now, what we're going to do here is break this r of t plus delta t into its three components. So that would be the limit delta t approaches 0 of f of t plus delta t I plus g of t plus delta t j plus, to two-dimension at first, okay, minus f of ti minus f g of tj. Then bring the f's together and the j's together, the i's and the j's, f's and the g's, the i's and the j's together. This one with this one, and that would be the derivative of f. That would be the derivative of f prime by definition. This would be the derivative of g prime j. That's what it is. The derivative of a vector value function is the sum of the derivatives of the component functions of each of the vectors. Hopefully just like you would expect, and just really straightforward. Just take the derivative of f, and that's the f, x component, the I component there, and then take the derivative of g, that's the j component. The scalar function of the derivative of the j component. Okay? So, what this leads down to, the important result is listed in the theorem below. If r of t is f of ti plus g of tj, where I don't know why that little vertical line shows up there. It's not in the book. It's I don't know what it's doing there, but I guess the typesetter just got something in there. Where f and g are both differentiable functions of t, then r prime of t is just f prime of ti plus g prime of tj. Just take the derivative of each component as you hit it, and you got it. That's in the plane. In space, r of t is f of ti plus g of tj plus h of tk. F, h, and j are all differentiable functions of t. Then r prime of t, f prime of ti plus g prime of tj plus h prime of tk. Just hopefully like you would expect. Take the derivative, the scalar derivative of the scalar functions, just like you normally did, but assign them to each of your vector directions. Okay? Note that the derivative of a vector value function r is itself a vector value function r prime. Okay? So if you're taking the derivative of a vector, you're going to get a vector. Even though you're taking the derivative of each of the components or scalars, they go with the vector, same vector that the function was. You can see from this figure, and yeah, I can see really clearly from this figure, that r prime of t is a vector tangent to the curve given by r of t and pointing in the direction of increasing t values. So if r of t is here and r of t plus delta t is there, then the r of t plus delta t minus r of t would be this vector here. That's your numerator vector divided by delta t, and as that delta t gets closer and closer to 0, these are coming back and being the tangent function. And notice that as t is increasing, r is going in that direction, so your r prime is going to be in the same direction as increasing t. It will be the slope of the tangent function at that point t. Okay. Just like it was for scalar functions. Make sense? Okay. So let's do one. For the vector value function r of t is equal to ti plus t squared plus 2j, find r prime of t. This will be a plane curve. Then sketch the plane curve represented by r of t and the graphs r of 1 and r prime at 1. So first, let's find r prime. So what is, oops, let me get my pen set up. Okay, what is r prime of t? You tell me. There's your r of t. Find r prime of t. I, you got it, plus 2t j. Perfect. Perfect. That's it. Okay? Then sketch the plane curve represented first by r of t. Okay? So let's do our curve here. Okay. Give me a t. 0, all right. And that'd be 0i. Okay, let me just knock off a few points here. Okay. So t equals 0 would be 0i, what else? T equals 0 would be 2j. We're just doing r of 0. So this would be right here. There would be your point where the term of the r of 0 would be right up there, pointing up there. Okay? Give me another t. 1. So that would be I plus 3j. So that would be right here. Right? Give me another t. Second? 2. So that would be 2i plus 6j. 3, 4, 5, 6, somewhere up here. So looking like it's going to be a parabola like this, right? Increasing this. Let's just see what happens if we go on the negative side. Negative, a negative 1, t equals negative 1, be a negative I plus 3j. Sure enough, it would be right here. So that's a parabola that does like this, and it's going in that direction. So there is your plane curve represented by that r of t. That was pretty easy, right? A little messy, but not bad. Okay? Then it said, sketch the graphs of r of 1 and r prime of 1. Well, r of 1, we just plotted it. There would be r of 1. Oops! I put a t there. R of 1. When t is equal to 1, that's where we were. Okay? Now it says do r prime of 1. Well, let's see what that is. R prime of 1 would be what? There's your r prime of t. R prime of 1 would be, it would be I plus, put a 1 in for t, plus 2j. Okay, 1 plus 2j. Well, that would be right 1 and up 2. Be right about there. And sure enough, that would be your r prime of 1. Okay? Right 1, up 1. And sure enough, that looks like that would be tangent to the curve of that. Okay? There you have it. Make sense? Well, let's see how their picture does. Can't be any better than mine. Well, they'll answer that question. Okay. Okay. First, differentiate, and you get I plus 2tj, just like y'all got. Okay. Then, it says for the position vector r of t, you can write the parametric equation x equal t and y is equal to t squared plus 1, which is fine. That's exactly what those parametric equations are. Corresponding rectangular equation is y is equal to x squared plus 2. Yeah. And that would be, when t is equal to 1, r of 1 would be I plus 3j, and r prime would be I plus 2j. And here they've done it all at once. Here's the vector r of t is equal to ti plus t squared plus 2j, which is exactly that shape we had before. The vector r of 1 is that one right here that goes from the origin to the point 1, 3, and then r prime of t was exactly pretty much what we did go right one and up two, and sure enough, that's it. Make sense? The thing is, for the R prime, you always put the origin. Don't put it down at the origin, put it at the point 1, 3 that you're measuring from. Sure enough, that looks tangent to me. Got it? Understood? Okay. The parameterization of the curve represented by the vector value function R of t is equal to f of ti plus g of tj plus h of tk is smooth on an open interval I when f prime, g prime, and h prime are all continuous on I, and r prime of t is not 0 for any value of t on the interval I. Okay. Now, why would r prime, could that not be 0? Can't quite think of any good reason it couldn't be, but that would just be a horizontal, not horizontal. That means it has no components. So r prime of t basically is hardly defined. So the only way that would be true is f prime of t was 0, g prime of t was 0, and h prime of t was 0, meaning each of these were constants to begin with. So this is just a point in space, and it's not going anywhere. So its first derivative is 0. So that's sort of a trivial case, but that's what we're dealing with. All right, so what we didn't do, and sorry I missed this, we didn't do example 2. So let's go back and do example 2. Okay? For the vectored value function, okay, r of t, vector function r of t is equal to cosine ti plus sine tj plus 2tk. Okay? Find each of the following. A. What is r prime of t? Not too bad. What would that be? Anybody? Negative sine ti. Next. Plus cosine tj. You need signs in between, remember that. Plus 2k. Perfect. B. What in the world would be r double prime t? Negative cosine ti negative sine tj. Done. There is no 0k. Nothing else. Okay. Now a fairly interesting problem. The C part says what is r prime t dotted with r double prime of t. R prime of t dot product with r double prime of t. Do you remember how to do a dot product? A dot product, you multiply these two together, but you lose these. Because you see, a dot product is always a scalar. This is going to be a scalar answer. So you multiply these two, add it to the product of those two. And add it to the product of those two, but what's the product of those two? This is a 0k, 2 times 0 is 0. So there is no k component. Well, there's no components at all.
Yeah.
So it's just 0. Okay, so the first, multiplying these two together, what do you get? Sine t cosine t. And you multiply those two together and you get what? Minus sine t cosine t. And what does that give you? 0. Sure enough, and this is basically always the case, a function dotted with this derivative is always 0. A function dotted with this derivative is always 0. Because, can I say always? I think so. Okay. Let me say it this way. A derivative of a function dotted with the second derivative is always 0. And the reason for that, the derivative is the velocity function you can think of, and the second derivative is the acceleration function, and those are always perpendicular to each other. Okay? So I think you can always say that. I think so anyway. How about this one? D. D is R prime crossed R double prime. R prime of t cross product with R double prime of t. I'm sorry? This is example 2 in the book. Yeah. Now, do you remember how to do a cross product? If it's a, say again? Cross product. You what?
I cross J is K.
Yeah, that's true. Okay, but here's, you have multiple. Here I'll show you the easy way. Okay? Now, this works only for 3-dimensional vectors. If you have 4-dimensional, whatever those are, it won't work. But 3-dimensional vectors, here's what you do. Right? Sort of like the determinant. Do y'all remember what determinant is? I'll show you. Of I, J, K, and then repeat the first two again. I, J. Okay? This is only for 3-dimensional. Won't work if it's any more. Won't work for it's any less, but there's an easy way to do it if it's 2-dimensional. Okay? And then you put the first vector components in there. So that would be minus cosine t under the I minus sine t. No, wait. Whoops. Wait. I looked at the wrong line. Sorry. I looked at the wrong line. Sorry. The R prime is minus sine t plus cosine t 2. Right? Then repeat the first two again. Minus sine t, cosine t. Okay? Then write the second vector. That's minus cosine t minus sine t, 0 minus cosine t minus sine t. Repeat the first two again. Okay. Now this isn't quite like a determinant. It would have been if I hadn't repeated those last two, if I just put a second line there. But here's how you do it. Go your down diagonals. That gives you, and multiply them together, that gives you 0, right? Do the next down diagonal, and that would be a minus 2 cosine t j, right? Then do the product of the third down diagonal, and that's going to be a plus sine squared t k. Right? Now, we go to our up diagonals, but these you're always going to subtract. Okay? So you subtract, and you got a minus here, so you're subtracting, so minus times plus, that's going to be a plus, and this is going to be a k, so that's going to be plus cosine, I can't write, let me see if I can get my pen to do better. Okay, that's hardly readable. Cosine squared tk. The next up diagonal is going to be a minus, which is plus 2 sine ti. So I'm going to put it here, 2 sine ti. And then the third up diagonal is going to be 0. You see? Because of that 0 at the bottom. So you add those together. I'm going to come up here and do it. And you get 2 sine ti minus 2 cosine tj. And then when you add these two together, what's sine squared plus cosine squared? 1 plus k. Okay? That's your cross product. Now here's a characteristic of the cross product. The cross product must be, it's a vector, always a vector. Dot product's always a scalar. The cross product's always a vector. Okay? Characteristic, it's got to be perpendicular both to this and to that. It's perpendicular to both of them. So one way you can check it pretty easily is do a dot product of these two. And what do you get here? Dot product. Minus 2 sine squared t minus 2 cosine squared t plus 2. Okay? So that was 2 sine squared t plus, no, it's a minus 2 sine squared t minus 2 cosine squared t plus 2. But factor out the minus 2 here, you get minus 2 times sine squared t plus cosine squared t plus 2. What's sine squared t plus cosine squared t? What's sine squared t plus cosine squared t? 1. Minus 2 times 1 is minus 2 plus 2 is 0. Sure enough, it's perpendicular to that one. So let's do the next one. Let's do this dotted with this one. What does this give us? Okay, negative 2 cosine sine. What do you get when you multiply these two together? Okay, can you multiply these two together? 0. And this is plus, that's minus 0. Yeah. So it is perpendicular to both of them. So that is your correct answer for your cross product, is that one up there. It's always a vector. And they got it in the book, right, 2, I think. 2 sine squared t, 2 sine ti minus 2 cosine tj plus k. Perfect. How are we doing time? Okay. So I think we're ready now for example 3. So let's scroll on down to get to example 3. We've already hit this slide. We already did it. I wasn't paying attention. And here's example 3. Now, what we got? Just over 10 minutes or less than 10 minutes? Huh? 5:14? Okay, so we got 11 minutes. Okay, so let's see if we can get example 3 done. Find the intervals on which the epicycloid C given by R of t is equal to 5 cosine t minus cosine 5ti plus 5 sine t minus sine 5tj is smooth. Okay, find the intervals on which that epicycloid is smooth. And what does it mean to be smooth? It's smooth whenever f prime, g prime, and h prime are continuous. Okay? So, guess what we need to do? Take a derivative. R prime, and we really don't need to know what R prime of t is, but we are going to do it because you do the derivative of this and the derivative of that. And where those are continuous, then this will be. So what's the derivative of 5 cosine t? Negative 5 sine t plus 5 sine, I can't write, trying to do sine and wrote cosine, okay, sine of 5t, okay, and that would be your I, and then the next plus, second, I can't hear. No, it's positive 5. Derivative of sine is positive. So 5 cosine t negative 5 cosine 5t j. Okay. Now, reminding ourselves again, top of the page, the parameterization, blah, 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 is smooth on an open interval when f prime, g prime, and h prime, this one doesn't have an h prime, are continuous on I. And r prime of t not equal to 0. Okay? Now first, both of these are continuous everywhere. Well, sines are, cosines are. So they are continuous everywhere. But the other feature is that it can't be 0, meaning this can't be 0 at the same place that is 0. So we need to sort of figure out where this is equal to 0. Well, where is that equal to 0? It's equal to 0 when 5 sine t is equal to 5 sine of 5t, right? If that's equal to 0, then add 5 sine t to both sides and you get that. And you could divide out the 5's and you get where sine of t is equal to sine of 5t. Okay? Now, those would be equal to each other anytime t is equal to 5t. Well, in other words, t minus 5t is equal to 0, so it'd be t times 1 minus 5 equals 0. That's minus 4t equals to 0. Okay. Or, goodness, that's going crazy, isn't it? Actually, a better thing to do where, yeah. Okay. Well, where is, are both of those equal to 0? At t equals 0, of course. But also, when t is any 2 by 2, let's see, well, minus 4t is equal to 0 as well. Or actually, we could have done it the other way and done 4t is equal to 0. There's no real reason to do minus. We could have done these in reverse order. 5t minus t is equal to 0, so that would be 5 minus 1, which is 4t is equal to 0. Okay? Now, obviously where t is equal to 0, but also where how to express this. When t, let's put it this way, 5t is equal to some 2 pi multiple of this, right? Because if t plus 2 pi, or 2n pi, is equal to 5t. Okay? So that would be 4t is equal to 2n pi. Okay? When is that going to be true? That's going to be when n is equal to 2 over pi. Okay, wait. T, let's do it this way. T is equal to okay. T is equal to n pi over 2. So all your half pi's, that would be where that is true. Okay? Then those are always going to be zeros. Let's do the same for cosine, and that would be where 5 cosine t is equal to 5 cosine 5t. Divide out the 5's, and you get cosine t is equal to cosine 5t, and that would be anywhere where the t is equal to t plus 2n pi, 2 pi n is equal to 5t, so 4t is equal to 2n pi. So you get to the same thing at all your half pi's. Okay? Now, but you're only going from 0 to 2 pi, so t has to be only there. So that would be t equals 0, pi halves, pi, and 3 halves pi, and 2 pi. Yeah. So those would be the ones, but the 0 and 2 pi are the same. And if you look at that, okay, I'm going to clear my stuff out of the way. Gosh, I'm running out of steam fast. Okay, so the derivative we did, they did, okay, got the same thing we did. The interval 0 to 2, the only values for which r prime of t is 0 plus that would be at t is equal to 0, pi half 2, yeah. Same ones we just came up with, and that would then be here, 0, pi halves, 3 halves pi, minus pi, 0, pi halves pi, 3 halves pi, and 2 pi, which is the same thing here. And you see this is indeed, that's where your derivatives are not continuous, because it's not smooth there, it's pointed. So those are the places your epicycloid, not smooth, where they intersect the axes at those points. So the intervals where they are smooth, 0 to pi halves, but not at pi halves to pi, but not at pi, or pi halves, pi to 3 halves pi, but not at either end, and 3 halves pi to 2 pi, but not at either end. So here's where it's smooth, there's where it's smooth, there's where it's smooth. So, okay. I think we've run out of time, haven't we? Awfully close anyway. So where are we? Differentiation of, Okay, we're going to be right in the middle of page 830. That's where we're going to end this thing today. And for some reason, I don't have my eraser out. Let's see if there's any homework problems for this one. I think there are a few. Let's see, we made decent progress. Do any of the odds 3 through 9, they're all at Calc Chat, 5's at Calc View. Do any of the odds 11 through 17, they're all at Calc Chat. Do either 19 or 21 or both, they're both at Calc Chat. Either 23 or 25, they're both at Calc Chat, 23's at Calc View. And then try to, like we just did, any of the odds 27 to 33, they're both at Calc, all at Calc Chat, 27's at Calc View. We'll stop there and pick up the rest of those later. Good deal. All right. That's the end of a long day. Goodness gracious. I've taught for almost 9 consecutive hours. I'm running out of juice. All right. Glad y'all were here. Any questions before you go? All right. I'll go on and end